All right, let's jump right in. We're tackling deep learning today, and you've given me a great place to start. This 100 deep learning terms explained from Geeks for Geeks.
It's really a glossary, but
Yeah.
instead of just, you know, defining terms, we're going to explore these terms. We're going to figure out what makes them interesting and why they matter.
I like that. So before we get into any of the specifics,
Yeah.
let's just lay the groundwork.
Sure.
What is deep learning? What makes it different than just like regular programming?
Well, think of it this way. In traditional programming, you write explicit rules for the computer to follow. But with deep learning, you're giving the computer a framework, a neural network, and a ton of data, and letting it figure out the rules for itself.
So instead of giving step-by-step instructions, you're
Right.
kind of giving it a nudge in the right direction.
That's a good way to put it, yeah.
And then letting it learn
Yeah.
from tons of examples.
Exactly. And the deep part refers to those multiple layers in the neural network. The more layers, the deeper the network, the more complex patterns it can learn
Okay.
from the data. It's like going from a simple single-story house to a skyscraper. Right? The potential for complexity increases dramatically.
I like that. So these neural networks, we hear about them all the time, and they're modeled after the human brain, right?
Right.
But how does that actually translate into a computer program?
Well, imagine a network of interconnected nodes, kind of like a giant web.
Uh-huh.
And each node receives input, processes it, passes it on to other nodes.
Okay.
It's a simplification of how neurons work in our brains, but this basic structure allows them to process information in really sophisticated ways.
So each of these nodes is like a mini processor.
Yeah.
And it's all working together to
create something much bigger?
create something much bigger.
Right.
Okay, so one of the things that you mentioned that I thought was interesting is the activation function.
Yeah.
What is that, and what role does it play?
Think of each activation function as a gatekeeper for its node. It decides whether the node should fire or not based on the input that it gets.
Okay.
It's like a switch deciding whether to turn on a light bulb. So one of the most common activation functions is something called ReLU, the rectified linear unit.
I love these names.
Yeah, they're great, right?
So ReLU, is it as complicated as it sounds?
Not at all. It's actually very simple.
Okay.
Imagine ReLU as a simple on-off switch.
Okay.
If the input is positive, the switch flips on and the node contributes to the output.
Okay.
If the input is negative, the switch stays off and the node doesn't contribute.
So it's either contributing or not contributing.
Yeah, you can think of it that way, yeah.
So if it's that simple, like how does that create this really complex decision-making process?
Well, while ReLU itself is simple, the combination of millions of these simple switches, all interacting across the layers of the network, creates a surprisingly nuanced and flexible system.
Okay, so we talked about how it processes information.
Right.
But how does it learn? How does it learn from the data that it's given?
So one of the key processes behind this learning is backpropagation.
Backpropagation?
Yeah.
What is that?
Well, it's how the network adjusts itself. It refines its understanding of the data.
So it's like retracing its steps.
Yeah, you could think of it that way.
Kind of like hitting rewind,
Yeah.
going back through and saying, okay, how did I get to that conclusion?
Exactly. It's all about analyzing the errors that the network makes and then going back through its layers, tweaking the connections between those nodes to improve its predictions.
So it's not just being told what the right answer is. It's
Right.
actually trying to figure out,
It's figuring out why it got something wrong.
why did I get that wrong?
Yeah.
And then adjusting accordingly.
Right. That's the beauty of it.
That is really cool.
This back and forth process, constantly learning from mistakes and refining its understanding, is at the heart of deep learning.
Okay, so we've got our network set up.
Yeah.
We're processing information. We're learning through backpropagation. How do we actually take all of this and do something useful with it?
Well, that's where we start to see the incredible diversity of deep learning applications.
Right.
But one area where they truly shine is image recognition.
Okay.
And the rock stars of image recognition are convolutional neural networks, or CNNs for short.
CNNs.
Yeah.
Okay, what makes them so special when it comes to images?
Well, think about how we as humans see an image.
Okay.
We don't just see a jumble of pixels. We see shapes, edges, textures.
Patterns.
Patterns, exactly. CNNs are designed to do the same thing. They have special layers called convolutional layers, that act like filters, scanning the image for these specific features.
So instead of looking at the whole picture at once, they're breaking it down into smaller parts.
Exactly.
And analyzing each piece.
Yeah, each convolutional layer looks for different features. And by combining the information from all these layers, the network can start to recognize objects within the image. It's like having a team of experts.
Oh, cool.
Each specializing in a different visual clue, all working together to solve a mystery.
I like that. Is that how Facebook is able to, like, tag people in pictures? It seems like magic, but now I'm starting to understand.
Exactly. Facial recognition is a prime example of CNNs in action, but it goes far beyond that.
Right.
Think about self-driving cars, identifying pedestrians and traffic signs, or doctors using AI to detect tumors in medical scans.
Wow.
CNNs are revolutionizing how we interact with the visual world.
Okay, so we've gone from these really basic building blocks to these incredible applications using CNNs, and I feel like we've just scratched the surface here.
We are, and the journey gets even more fascinating as we explore how these networks are trained and optimized to perform these tasks with incredible accuracy.
Okay, well, let's come back in our next part and dig into that, because that's what's so cool about these deep dives. There's always another layer to uncover.
Absolutely.
So we'll be back soon to explore more of the training process.
Great. Can't wait. Welcome back. Now let's get into the nitty-gritty of how these deep learning models are trained and optimized.
All right, so we've built this neural network. We've got these layers. We got the connections. It's all set up, but it's still a blank slate, right?
Right.
How do we actually teach it to do something useful, like recognize a cat in a picture or translate languages?
That's where the training comes in.
Yeah.
Imagine you're teaching a child to ride a bike.
Right.
You wouldn't just hand them a textbook.
Right.
And expect them to become a pro. They need practice. They need feedback.
Yeah.
They need to learn from their stumbles.
So we're not programming the knowledge in.
Right.
We're actually letting the network learn.
Exactly. We feed the network massive amounts of labeled data.
Okay.
Images, text, audio, whatever it needs to learn, and let it figure out the patterns and relationships within that data.
So it's really learning by doing, but on a massive scale.
Exactly.
This data isn't just thrown at it all at once, though.
Right, that's where the concept of epochs comes in.
Epochs.
Yeah, think of an epoch as a training session, a complete pass through the entire data set.
Okay.
But it's not just a mindless repetition. The data is divided into smaller batches, and the network learns from each batch, making adjustments and refining its understanding with every step.
So each epoch is kind of like a lap around the track.
Yeah, I like that analogy.
And it's getting a little faster,
Yeah.
a little more efficient each time.
Exactly. And to track the network's progress during these training sessions, we use a loss function.
A loss function. Yeah.
So we're measuring how much the network is losing during training.
It might sound strange, but think of it this way. The loss function calculates the difference between the network's predictions and the actual values.
Okay.
It's a measure of how far off the mark the network is. The goal is to minimize this loss, to get as close to the true values as possible.
So it's kind of like aiming for a low score in golf.
Perfect analogy.
Nice.
And to fine-tune this performance, we need to set the right learning rate. Okay, so the learning rate, we're controlling the pace. How fast?
Exactly. Imagine you're learning a new language.
Okay.
If you try to cram too much vocabulary too quickly, you might get overwhelmed and forget everything.
Right.
But if you go too slow, it might take forever to become fluent.
So we have to find that Goldilocks zone.
Got it.
Not too fast, not too slow.
Exactly. A high learning rate means the network can learn quickly, but it might miss subtle patterns or overshoot the optimal solution. A low learning rate is more cautious, but it can take a long time to converge on the best solution.
So how do we fine-tune this? How do we make sure we're not going too fast or too slow?
Well, that's where optimizers come into play.
Optimizers.
These are algorithms designed to help the network adjust its weights and biases more efficiently, guiding it towards peak performance. Think of them as the coaches of the deep learning world. Constantly analyzing the network's performance and tweaking its training regimen.
So instead of us manually doing that, we've got these optimizers who are acting like personal trainers.
Exactly.
Okay, are there different types of optimizers?
Yeah, there are actually a variety of optimizers.
Okay.
Each with its own strengths and weaknesses.
Yeah.
One popular example is the Atom Optimizer.
Atom Optimizer?
It's known for its efficiency and its ability to handle noisy data,
Okay.
making it a great all-around choice
Okay.
for many deep learning tasks.
So Atom Optimizer is like that star quarterback coach, right?
Right.
Known for getting the best out of their team.
Yeah, I like that.
So we've got the training data, the epochs, the loss function, learning rate, optimizers. It's like this whole ecosystem to guide the learning process.
You're getting it. It's a beautiful dance between data, algorithms, and computational power.
Yeah.
But like any complex system, deep learning isn't without its challenges.
Right.
There are pitfalls to avoid, and understanding these potential roadblocks is crucial for success.
Okay, give me a reality check here. What are some of the challenges that can trip up even the most sophisticated deep learning model?
One of the most common challenges is overfitting. Imagine you're studying for a history test by memorizing every single date and name in the textbook.
Okay.
You might ace that specific test, but you haven't really learned the underlying concepts.
So we haven't actually understood it.
Exactly. That's essentially what happens with overfitting.
Okay.
In deep learning, the network becomes so good at recognizing patterns in the training data that it essentially memorizes the answers.
Okay.
But when it encounters new data it hasn't seen before,
Yeah.
it struggles to generalize and make accurate predictions.
So it's become too specialized.
You could say that, yeah.
In what it's learned.
Yeah, overfitting is like creating a key that fits perfectly into one lock, but can't open any others.
I like that. So how do we avoid that?
One common approach is to use a technique called regularization.
Regularization.
Yeah, think of it as adding a penalty for complexity. We essentially discourage the network from creating overly complex models.
So instead of letting it build the most elaborate, intricate model,
Right.
we're saying, hey, try to simplify a little bit.
Yeah, keep it simple.
Find a more elegant solution.
Exactly. By simplifying the model, by reducing the number of parameters or connections, we make it more robust and less prone to overfitting.
Okay, so we talked about overfitting where the network learns too much,
Right.
gets too specialized. Is there the opposite problem where it doesn't learn enough?
Yeah, great question. The opposite of overfitting is underfitting.
Underfitting.
This is where the network is too simple,
Okay.
too basic to capture the complexities within the data. It's like trying to understand a symphony with only a single note.
So it hasn't really dug deep enough.
Exactly. Underfitting means the network hasn't learned enough to make accurate predictions.
Okay.
It's like trying to build a house with only a hammer and nails.
Right.
You need a wider range of tools and techniques to create something truly robust.
So we've got these two extremes, overfitting and underfitting.
Right.
You've got to find that balance.
You've hit the nail on the head. It's a constant balancing act.
Yeah.
And it often requires experimentation and fine-tuning to achieve the best results. But once we've tackled these basic challenges, we can start to explore some of the more advanced techniques
Okay.
that are pushing the boundaries of deep learning.
Let's do it. The article that you provided mentioned transfer learning and generative adversarial networks, or GANs.
Oh, yeah. Those are great.
As some of these more advanced techniques.
Yes, definitely.
What makes them so special?
These are some of the most exciting areas of deep learning, and they're opening up incredible new possibilities. So let's start with transfer learning. Imagine you've spent years learning to play classical piano.
Okay.
Now you want to learn jazz. Do you have to start from scratch?
No.
Forgetting everything you've learned about music theory and technique?
You build on what you already know, right?
Exactly. That's the essence of transfer learning in deep learning. Instead of training a network from scratch for every new task,
Right.
we can leverage the knowledge gained from previous tasks.
Cool.
We take a pre-trained network, one that's already learned a lot about a particular domain, and fine-tune it for a new related task.
So we're giving it a head start.
Exactly. It's incredibly efficient.
Yeah.
One area where transfer learning is having a huge impact is in natural language processing, or NLP.
Okay.
We can take a network that's been trained on a massive data set of text, like all of Wikipedia,
Wow.
and fine-tune it for tasks like translation, sentiment analysis, or even writing creative content.
So we don't have to teach it how to understand language from the beginning.
We're leveraging its existing language skills.
That's awesome. And what about GANs?
GANs, or generative adversarial networks, take a completely different approach.
Okay.
Instead of just recognizing patterns, they're actually creating new data.
Okay.
Imagine two networks locked in a creative battle.
Okay.
One network, the generator, is trying to create realistic data, like images or music. The other network, the discriminator, is trying to spot the fakes.
So it's like a game of cat and mouse.
Exactly. This adversarial process pushes both networks to improve. The generator gets better at creating more realistic data, while the discriminator becomes more discerning,
Wow.
more adept at identifying the subtle cues that distinguish real data from fakes.
That's amazing. What are some practical applications for this?
GANs are being used in a really diverse range of applications. They're creating photorealistic images and videos, generating music in different styles, and even enhancing old photographs and videos, bringing them back to life with incredible detail.
Wow. Okay, so we've gone from teaching networks to recognize patterns to now teaching them to create, to be artists, basically.
Pretty amazing, right?
Yeah. But why should we care about all this as just everyday people? How is it impacting our lives?
That's a great question, and it's one that everyone should be asking.
Right.
Deep learning is no longer just a futuristic concept confined to research labs. It's already woven into the fabric of our daily lives.
Okay, give me some concrete examples.
Well, think about the personalized recommendations you get on streaming services or online shopping platforms. That's deep learning at work. Analyzing your past behavior and predicting what you might enjoy next.
Yeah.
Or consider the voice assistants that we interact with on our smartphones and smart speakers. They're powered by deep learning algorithms that allow them to understand and respond to our commands.
Okay, so this isn't just like
It's not just futuristic.
cool technology demos. It's actually stuff that we're using every day.
Exactly, and it goes far beyond that. Deep learning is revolutionizing healthcare, allowing doctors to diagnose diseases earlier and more accurately.
Wow.
It's transforming transportation, with self-driving cars poised to reshape our cities
Okay.
and our commutes. And it's even being used to address some of the world's most pressing challenges, from climate change to
Right.
poverty.
Wow, so it's really having a profound impact on almost every aspect of our lives.
Absolutely. It's a powerful tool, and like any tool, it can be used for good or for ill. That's why it's so important for everyone to have a basic understanding of deep learning,
Right.
to be aware of its potential benefits and risks, and to engage in the conversations shaping its future.
I completely agree. This deep dive has been amazing. I feel like I've got a much deeper appreciation for all of this.
It's been a pleasure exploring these concepts with you.
But there's one term from the article that keeps popping into my head, and I know you mentioned it briefly, but I want to circle back to it.
Sure.
Zero-shot learning. How can we possibly teach a network to recognize something it's never encountered before?
Ah, yes. Zero-shot learning.
It sounds impossible.
It's one of the most intriguing and potentially revolutionary frontiers of deep learning.
Yeah.
It's the idea that we can teach networks to recognize and understand things they've never encountered before.
Okay.
To understand zero-shot learning, we need to shift our perspective a bit. Think about how humans learn. We don't need to see a million labeled images of a zebra to recognize one in the wild, right?
Right.
We learn by understanding concepts.
Right. Stripes, horse-like, African savanna.
Exactly. And zero-shot learning aims to replicate this in machines.
Okay.
Instead of feeding the network labeled images, we can provide it with descriptions, attributes, or relationships.
Okay.
For instance, we might teach it that a zebra has black and white stripes, is a type of mammal, and lives in Africa.
So we're basically giving it a vocabulary of concepts and then letting it figure out how to apply those?
Precisely. The network needs to learn how to connect those textual descriptions with visual features. It's almost like teaching the network to understand language and then use that understanding to interpret images.
So it's not just matching pixels, it's really going deeper than that.
That's the goal.
Wow. That's incredible.
And this opens up some really exciting possibilities. Imagine a network that can identify new species of plants or animals based on descriptions or diagnose rare diseases from symptom lists.
It sounds almost too good to be true. How far along are we with this?
It's still early days, but the progress is really encouraging.
Okay.
Researchers are experimenting with different approaches. Some are using knowledge graphs to connect concepts and build a semantic understanding.
Okay.
Others are training networks on multimodal data, combining text, images, and even sounds to create a richer learning experience.
Multimodal data, so it's kind of like giving it a more...
A more holistic view of the world.
Just like we experience it.
Exactly.
This is so cool. But it also raises some interesting questions, right? Like, if we're teaching networks to think like us, are we on the verge of creating truly intelligent machines?
That's the big question, isn't it?
Yeah.
But it's important to remember that deep learning,
Yeah.
even in its most advanced forms, is still a tool. It's a powerful tool with incredible potential. But it's up to us to guide its development and ensure it's used for good.
So it's not so much about the technology itself,
Right.
it's how we choose to use it.
Exactly. As we venture further into the realm of artificial intelligence,
Right.
we need to be mindful of the ethical implications and ensure that these technologies are aligned with human values.
That's a really good point. Let's take a quick break. When we come back, we'll unravel the mysteries of this groundbreaking approach to zero-shot learning and explore how it's pushing the boundaries of what's possible with deep learning. Stay tuned.
Sounds great.
All right, we're back, and I have to say my mind is still kind of blown from that whole Jan's thing.
Yeah, it's pretty wild stuff.
But let's jump back into zero-shot learning. How is it even possible to teach a network to identify something it's never seen before? Just doesn't compute for me.
Well, it's not magic, but it does feel like it sometimes. To really grasp zero-shot learning, we kind of have to change how we think about, think about it this way. We don't need to see thousands of pictures of a zebra with the label zebra to know what one is when we see it, right?
Right, we just kind of know.
Exactly. We figure it out through concepts, stripes, horse-like, African animal. You get the idea.
So it's more about understanding the bigger picture than memorizing specific examples.
That's it. And that's what we're trying to recreate with machines using zero-shot learning. Instead of giving the network tons of labeled pictures, we give it descriptions, attributes, relationships, stuff like that.
So instead of this is a zebra, it's more like zebras have stripes, are mammals, and live in Africa.
Exactly. The network has to learn to connect those words with the actual visual features of a zebra. It's kind of like teaching it a language and then making it use that language to understand pictures.
So it's really going beyond just looking at pixels. It's actually trying to understand what a zebra is.
That's the goal. And think about the possibilities. A network that can spot a new species of plant or animal just from a description, or one that can diagnose a rare disease based on symptoms.
That sounds amazing. Is it actually working, or is this mostly theory at this point?
It's still early, but there's been a lot of progress. There are a few different ways researchers are going about it. Some are using what are called knowledge graphs to connect concepts and build this semantic understanding.
Knowledge graphs.
Yeah, think of it like a map of how different ideas relate to each other. Others are using what's called multimodal data, basically combining text, pictures, even sounds to create a richer learning experience for the network.
Multimodal data, so giving it a more well-rounded view of the world.
Exactly. Just like how we experience things through multiple senses. The closer we can get to that, the better these networks will get at learning and reasoning like we do.
I gotta say, this is all really exciting stuff, but it's also a little mind-blowing to think about. If we're teaching these networks to think like us, what does that even mean for the future? Are we talking about truly intelligent machines?
That's the big question, right?
Yeah.
But here's the thing. Deep learning, even the most advanced kind, is still a tool, and a really powerful one. It has amazing potential, but how we use it, how we guide its development, that's what really matters.
So it comes back to us, to making sure we're using this technology for the right reasons.
Absolutely. As we keep exploring AI and deep learning, we got to be careful, got to consider the ethical implications, and make sure we're not just creating something powerful, but something that benefits humanity.
It's been an incredible deep dive, I have to say. I've learned so much about the world of deep learning, from the nuts and bolts of neural networks to these mind-bending ideas like zero-shot learning.
It's been fantastic exploring all this with you. Deep learning's always changing, always growing, and there's always something new to learn. But I hope this deep dive has given everyone a solid foundation and maybe sparked some curiosity to keep digging deeper on your own.
It definitely has for me. And who knows, maybe someone listening will be the one to make the next big breakthrough in AI.
Keep asking those questions, keep learning, and keep diving deep.
Thanks for joining us on this deep dive into the incredible world of deep learning.